the discussion that then follows in the panel discussion of these four folks who I will introduce at that point in time and whose names you see on the program. They are the centerpiece of the conversation, or at least the preponderance of the duration we've got in these 2 hours. We'll have a good long time for the four of them, both among themselves and then in questions from those of you here in the audience afterward, to develop this question about industry's unremarked role in the Apollo program. We will close, I think, right on time at 12:30. So those of you who are asking questions or want to get a question in during that segment of the program, please help me pace yourselves, your questions, your answers, so that we can move on with the day after 12:30. Okay. That's as much as I need to say right now, other than to introduce Bob Stevens. Bob Stevens, if there be a captain of industry worthy of the term, it is Bob Stevens. He is the former, now retired chairman and chief executive officer of Lockheed Martin, and had a long career, you can rest assured, all the way back to his education in the aerospace industry. As I say, he gave me some decisive help in organizing the program. And one of the voices that I wanted to bring and put right at the front of the program was that of a captain of industry to, as I keep saying, set the tone for what we want to do today. All of the speakers and panelists' bios in much greater detail than you're going to hear out of any of our mouths are available to you, and I hope you will pour through them if you're not familiar with these folks. But I don't think Bob would want me to belabor his introduction much more than that, and to welcome him to the stage. Thank you, Bob. Please, Steve.
Thank you, Steve. There's probably no better title than retired captain of industry, let me assure you, other than perhaps being a board member here at the Atlanta Council, and I'm very proud to do so. I've been so very impressed over many years now with the work that's done here at the Council as they bring together the communities of global leaders. And in the discussions that occur here that are very candid, very open, very forthright, they are not conversations for the sake of enriching dialogue, but the professionals who work here at the Council clearly extract from each of these engagements the salient features and then weave together through some very innovative thinking new ways for us to think about sustainable strategies that will help us guide ourselves through periods of uncertainty or better policy formulation so we really get outcomes that are more meaningful, or even better governance principles that help weave together the international community in which we all live and work. So I thank the professionals who work here at the Council for sure. Steve mentioned that this program, the Captains of Industry series, is part of the Scowcroft Center for Strategy and Security. As we talk about the context for Apollo, the kind of thinking that goes on here at the Council and at the Scowcroft Center, led by Barry Pavel and his team, is to note the context in which Apollo occurred, which was clearly a time of great power competition during the Cold War between us and the Soviet Union. And Barry and his team have clearly recognized that there are some features in the environment today where we see the emergence of great power competition. So through the balance of 2019 and 2020, the Scowcroft Center team will continue to evolve the thinking that may help us navigate a difficult and demanding time that's coming toward us. I was born in 1951, which was, turns out, a great year to be born if you wanted to be influenced by the work of Project Apollo. And I was first exposed, like so many other kids of my generation, to these flight test programs that were occurring at Edwards Air Force Base that always looked so exciting, taking airplanes to their out of bounds, that evolved into Projects Mercury and Gemini and Apollo. So I'm very sure that the influence of those early days, to me, inspired, for me, a career of 40 years in the aerospace industry. And that's a career over which I have not a single second of regret, because I had the opportunity to work on programs that I believe were genuinely significant, programs that really enriched our understanding of ourselves, our planet, where we've been, where we're going, the solar system, the universe, or systems that provide better services for citizens, and provide for our security and the security of friends and allies around the globe. Probably more than that, though, for me, were the quality and the character of the people that I had the opportunity to work with. One of those people is on the panel today. It's Jack Clemens. I'm really privileged to call Jack a friend, and you won't find a better systems engineer than Jack Clemens. I also, over the years, to me kind of remarkably and unexpectedly, developed a friendship with Neil Armstrong. It was in fact Neil Armstrong who taught me, in conjunction with a gentleman named Larry Kitchen, who used to be the CEO of Lockheed Martin, the fundamentals of fly fishing. Anyone who's tried their first hand at fly fishing will recognize it was a much better day for me than it was for them. But it was also Neil Armstrong who gave me the absolute very best description of the kind of teamwork that was necessary to accomplish the goals of projects like Apollo. I introduced him at the Air and Space Museum one evening where he gave remarks. And I suspect it was very routine for Neil that the first comments and almost all the early comments were all about him. You're the person, you're the guy, you're the man, you're the first one, you're the one. And his answer, and I wish I could remember the exact words, but I'll paraphrase, he said there were 400,000 people working on the human spaceflight program. I was but one of them. I had a series of tasks that I had to master, and I worked very diligently to do that. But me and my astronaut colleagues went to every NASA site, went to every contractor facility, went to every industry location, and we encouraged every one of those people to set the same high standards and to master their parts of this task. And the great pleasure that I, Neil Armstrong, have today is I was a member of the team of people that went to the moon and safely returned to Earth. And the standard of excellence here is we accomplished all the goals that we set out for us. And that notion of the nature of the team sport and how to organize individuals, motivate, and lead them to accomplish great goals has stayed with me since he made those remarks. So I hope you will enjoy the discussion that the panel has today, because I'm certain it will illuminate these subjects more clearly. It's now my pleasure to introduce Don McMonagle, who is a retired United States Air Force colonel. He is a fighter pilot. He is a test pilot. He is a NASA astronaut. And he's a distinguished industry executive who's accumulated a huge volume of personal experience in all things space systems. So please join me in welcoming to the podium Don McMonagle. Thank you.
Well, first of all, let me thank Steve for inviting me here and fully understanding the concept of a captain. I want to thank Captain Stevens for his kind remarks and introduction. Many would argue that the reason we went to the moon was to win a space race. It was all about the race. It was all about the competition with the Russians to get there first. But I believe, as I look at videos and documentaries of the Apollo 11 program, that began to meld into a discussion around mankind and the comment that Steve used up front here. The concept of mankind, and we do this for all mankind, that is what's on the plaque that's on the Apollo 11 Eagle vehicle that sits on the moon. It says, "We came in peace for all mankind." It's signed by the 3 astronauts and the President of the United States at that time, President Nixon. And it amplified the idea that this wasn't about the United States specifically and winning the space race. It became bigger than that. It became about mankind's ambitions, and it became about mankind's nature to explore. Now, I live in Tucson, Arizona on weekends when I get home from travel, and there are a lot of rocks in Tucson. So the idea that we brought back 47.5 pounds of rocks from the moon on Apollo 11, was that truly the payload that we went to get? I would argue that the rocks weren't important as the idea that we did the trip to the moon, we accomplished that feat because we have an innate nature to explore. And we have to see it with our own eyes. We have to touch it with our own hands. And unless you do that with the human presence, you're not truly doing the rich exploration and the acknowledgement of what it takes to truly fulfill our need. Neil Armstrong called it a giant leap, but he also called it for mankind, but I would say that it also gave us a huge lesson in humility. The fact that we could demonstrate that Copernicus, Kepler, and Galileo were all correct in determining that we weren't the center of the universe, but we also proved we also proved to ourselves by looking back at the earth and recognizing that we're going to another heavenly body, that in the perspective of the universe, we got humbled by the fact that we actually live on a relatively small planet in an average-sized solar system at the edge of an average-sized galaxy in an infinite universe. We are mere specks in the grand scheme of things. It humbled us. It gave us perspective about our existence as living creatures. I would argue that it was both a quest for knowledge and a demonstration of our capabilities as humans. And as the captain has described, it was a team sport. And it could not have been accomplished without the collective efforts of those in the government who were responsible for orchestrating this magnificent achievement, but also the plethora of industry partners that had to perform with the perfection that Neil Armstrong demanded of them, as all astronauts expected of the industry. And there are many who participated, just to name a few. The Stage 1 was built by Boeing at the Michoud Assembly Facility in New Orleans. The Stage 2, Northrop Grumman Aviation in Seal Beach. Saturn IV was built by Douglas Aircraft Company in Huntington Beach. The instrument unit, or the brains of the system, built by International Business Machines, IBM. The Columbia service module and command module, built by North American Rockwell. The landing vehicle, built by Grumman. And these are just a handful of the prime integrators for each of those major components. And then there's a whole host of contributors and industry participants that contributed thousands of components and thousands of levels of expertise. They all had to build new materials. We couldn't go to the moon with the weight of the systems that existed at the time. We had to figure out how to build them smaller, lighter, make them more efficient, make computations faster, new software, new operational concepts, new ways of testing things, new ways of training astronauts. I was interested to learn that Raytheon's contribution, one of their major contributions to the Apollo program, was the Apollo guidance computer that led us to the surface of the moon. That Apollo guidance computer was a remarkable miniaturization of a box about the size of this piece of paper and about 2 inches thick that held an amazing 2 kilobytes of memory. And that 2 kilobytes is what did the computations that got us to the surface of the moon. And also, to create those 2 kilobytes, there weren't semiconductors. It had to be interwoven, wired memory systems that were sewn together with seamstresses to make that box work. Whatever it took, it was done. Everyone remembers watching the video broadcasts that came down, everyone that was alive at that time. Many of you are just too young, sorry. But I watched it live. I was 17 years old at the time, and I was a junior in high school at the United States Coast Guard Academy getting an orientation to Academy life. And I remember taking a break from that orientation where they had us marching up and down the halls and rowing boats, but they put us in their conference room. We sat down in a room similar to this with a black and white TV set about this big in the front of the room, and we watched Neil Armstrong step on the surface of the moon. I did not know at the time that it was a microwave Raytheon Amplitron that was enabling those broadcasts from the surface of the moon back to the Earth. That was state-of-the-art technology that led 1 billion people on this planet to be able to see that image in real time, including myself. Now, carry that legacy forward. It wasn't until I was detailed from the Air Force to NASA as an astronaut that I became fully aware of industry's role in the Apollo and the exploration program. I was introduced into the astronaut program in 1987. So when I got there, we were seeing the shuttle program just in its ramping up, which started in 1981, 9 years after the last Apollo mission, which concluded in 1972. Now, in that role, there were legacy terms that I said, why do we use the term Capcom for the person who communicates to the space shuttle? There is no capsule in the space shuttle, but they use the term capsule communicator, or Capcom, for those of us who communicated with the astronauts in orbit, a legacy. When I looked at the keyboard in the space shuttle program to enter the data into the general purpose computers, by the way, These were the upgraded general purpose computers that had 256K of memory in those computers. And those keyboards looked almost identical to the keyboard that was used to interface on the Apollo Eagle lander to the Apollo guidance computer. Legacy, 15 years later, same keyboard, same entry. I also was impressed that the operational philosophies that we were adopting, that we were propagating in the shuttle program, as we discussed a little earlier, were the same operational philosophies used in the Apollo program. Understand what your risks are. Get all of them identified. Find them before they bite you. And then figure out how to bound those risks to understand what the limits are. And then from there, assess the risk, put in the mitigations to the risk that you can, and if the residual risk is acceptable, accept that risk to take the risk going forward. Now, the shuttle program, it was hard to get risk accepted. In the Apollo program, they took a lot of risk. And I'm worried that risk aversion could be an inhibitor to us continuing the spirit of exploration and the new technologies we will need in the future. I was given an additional duty once I finished my astronaut candidacy after a year. My first additional duty, because I had a mechanical engineering master's degree, was to be the astronaut's representative to the space shuttle main engines, to the propulsion system, and to the external tank. A lot of mechanical equipment. And I was excited when I was invited to go to the first propulsion system integration working group, the PSIG, as they called it. We sat down in a conference table. We had a teleconference communicator in the center of the table, and the NASA engineers that I had held in tremendous regard as the knowledge of all things space dialed up Rockwell Downey Rocketdyne and asked about a unique problem with the space shuttle main engine shutdown sequence, where they were getting miniature explosions inside the engine after shutdown, called pops, that they wanted to understand and know what the risk was for an engine coming apart in a shutdown sequence on launch. When they dialed up Rockwell Downey and Rocketdyne, the Rocketdyne engineer came up on the call, and the NASA engineer asked him, how do we handle this situation? Explain it to us. How do we handle it? My whole concept about industry's involvement reversed at that moment, in that the engine behind the knowledge and the engineering skills that built the shuttle and logically built Apollo came from industry. And from that point on, I recognized that industry was the engine. And in true, industry is the engine behind human ambition. The government orchestrates it, but industry generates it. And that's where the knowledge, the technology, and some of the skills of manufacturing lie. It lives on. The future demands of industry is going to demand the same level of pursuit of excellence as we've had in the past. And when I was a manager within NASA, I remember 15 to 30 technical issues leading up to every launch that I had to resolve in leading up to those launches. The excellence that I had to demand of the contractor workforce was the way that we got to risk acceptance and continued operation of the shuttle program. That demand for excellence continues today. Raytheon is involved in that as well. At the Neutral Buoyancy Laboratory at Johnson Space Center, there's a pool of 6 million gallons of water where a space station is underwater, and the choreographing of every activity that takes place during spacewalks is choreographed, planned, demonstrated, tested, and revised if necessary in that Neutral Buoyancy Laboratory. We're going to need that kind of innovation capability and training and testing capability as we go forward, because there will be microgravity environments near asteroids. There will be 1/6 gravity on the moon. Eventually there will be 1/3 gravity on Mars and other moons that may have other variable gravities. The innovation of using a neutral buoyancy laboratory or a variable buoyancy laboratory is going to be technology we need in the future. I have observed that space capabilities are increasing almost at the rate of Moore's Law. They almost double every year. And I know of the intent of various launch vehicle providers of launching upwards of 12,000 satellites into low Earth orbit. How are we going to keep track of all of those space vehicles and know whether or not they are in conflict with other trajectories of other space objects and prevent collisions? Space traffic management requires high-speed computing. Raytheon's involved with that as well in terms of how to upgrade the computers and the computations taking place at the Space Data Operations Center. Real-time imagery will come out of those satellites. Real-time capability to do high-speed internet from low Earth orbit satellites that don't have latency like the geostationary satellites. All of this will come from the space development. I currently manage a program within a joint venture that deals with the Air Force Space Launch Ranges. So we run the range at Cape Canaveral and the range at Vandenberg Air Force Base for the Air Force. How do we get to a launch rate that launches all of those satellites, turn the range from one operation to the next, and handle what is anticipated to be 100 launches a year off of these ranges that in the past have only had to deal with 8 to 15? All of that technology is what we're working on to handle the future and what we will need for high reliability and instant reconfiguration and the operations tempo that goes with those types of ranges. I would tell you that as a child, even when I was in elementary school, there was this president that said, why don't we launch to the moon and return a man safely from the moon? And I was only about 10 years old at the time. And I said, go to the moon. That sounds cool. That was a word that we used then, cool. But I had no idea how to do that. And I didn't know that anyone else knew how to do that. And I think, frankly, there weren't anybody that really knew how to do that. But over the next 10 years, they figured it out. Now the concept is, let's take human to Mars. Well, to use maybe an upgraded term, I would say that's rad. Why don't we do that? But I would also say there are real concerns about that. We don't know how to get to Mars. We don't know how to handle the propulsion systems that would get there faster than 6 months. We don't know how to handle the radiation environment of deep space. We don't know what surface construction tools we're going to have to build and construct on the surface of another planet. We don't know what the logistics is going to be like if it takes 6 months to get there. What are the logistics challenges that go with that? It's going to require the best of industry in a team sport. And I would argue also that our maker gave us a moon. They gave Earth a moon. And that moon appears to be the place where we can demonstrate how to handle the challenges for a Mars mission on our nearby island, we call the moon, before we attempt to cross the solar ocean to Mars. And that being the case, let's do the moon again, now, and use our moon as a training ground to get ready for that ocean voyage in the near future. It will be hard. President Kennedy told us we don't do it because it's easy. We do it because it's hard. But we can't do it without the aerospace industry. Are we ready? Thank you very much.
Terrific. Thank you. Thank you so much. All right, I will now invite this panel to take the stage, take the seats that you've been assigned. Please come right up. Once they are settled, I will make introductions of them. John, David, Jack. Come right up. I'll work from right to left because I want to end with Teasel, who's going to moderate the panel. John Tilko, on your right, is the Chief Innovation Officer at Aurora Flight Sciences, a Boeing company. Also a lecturer at the Department of Aeronautics and Astronautics at Massachusetts Institute of Technology, where he teaches, or certainly did, engineering Apollo. The rest of his bio you can read here, but just that, particularly the fact that he teaches engineering Apollo at MIT, testifies to what is true of all of these panelists. They are into this. This is, we will stop at 12:30, but they've assured me they can go till 5 on this topic and maintain your interest if needed. So So the guy who teaches engineering Apollo at MIT is one of the panelists. David Mindell is a professor of aeronautics and astronautics and the Dibner Professor of History of Engineering and Manufacturing at MIT. He's also the Chief Executive Officer of a very interesting company, a micro-location company whose business is based on micro-location technology. It's called Humatics, and he's the author of, among other books, Digital Apollo. I think some of the guidance and control that Don mentioned may come back into our conversation. Jack Clemens, whom Bob Stevens mentioned and helped me, thanks again, make a connection with, is the former lead engineer supporting operations at NASA's Manned Spacecraft Center with then TRW. He's also the former senior vice president of engineering at Lockheed Martin and the author of Safely to Earth, which I also commend to your attention if this conversation interests you. Aha, there we go, fair enough, fair enough. Yeah, thank you, David. I was wondering if you were going to hold back. One of the things that I very much wanted to bring to this panel was someone who was there, someone who worked on this program. Jack, as he will explain, worked on the Apollo program as a young engineer at TRW. And then finally, but hardly least, Teasel Muir-Harmony. Thank you, Teasel. She is no less than the curator of Apollo spacecraft at no less than the Smithsonian National Air and Space Museum. She herself is the author of a book with the term Apollo in its title, Apollo to the Moon. I'm going to turn the further conversation, which we're going to have for about an hour before taking questions from those of you here in the audience, to Teasel. Thank you very much.
Thank you so much. So as a curator, I get to interact with people quite a lot, and I get to talk about Apollo, which is wonderful. And when you ask people, how did we get to the moon, and who went to the moon, how did it happen, you usually get answers about the US or NASA, but that's not the full story, and that's part of what we're talking about today. So to start off, I want to have a little quiz. So it's been mentioned that roughly 400,000 people were working on Project Apollo by the mid-1960s. Any sense of what percentage of that workforce came from industry? I have a feeling this group might get it, but it's over 90%. To give you a sense of the scale, it's quite significant. So about 376,000 of those 400,000 were coming from industry. Between 80 and 90% of NASA's budget was going to contracts. Okay, so it's on a huge scale, and it's an area of the history of Apollo that we often don't focus on when we're talking about it, and it deserves much more attention. So in order to talk about this, I'm going to focus on an artifact, because that's what I do. So I'll show you a picture of it here. This is the mobile quarantine facility. You can see it over there as well. Yeah. So focusing on the role of private industry will tell us a lot about how Apollo was done, how it was done in such a short timeline, and how getting to the moon became a reality. So we often think of first, like traveling the distance to the moon, or the speed, or rendezvous and docking, all these different capabilities. But management of complex structures, the complexity, the rate of growth, and technological sophistication are all tied to this story of industry in Apollo. So when Kennedy proposed Project Apollo, it drew on huge financial resources and also a huge workforce. And it's worthwhile to remember that when Kennedy proposed Apollo in 1961, NASA had only been around for a few years, since 1958. And the basic approach that was taken was that NASA would determine the requirements for new technology and a timetable and put the project out for bid. NASA focused on managing and unifying what became many different programs and facilities spread across the country. So NASA grew from 10,000 employees in 1960 to 36,000 in 1966. But the contract workforce grew from 36,000, roughly 36,000 in 1960 to 376,000 by 1965. So take a look at the mobile quarantine facility. Hopefully it looks familiar. And that's an important part of the story. And that's one of the things I like to do working with artifacts, because the physical characteristics can tell you a lot about the history itself. And The fact that it looks familiar is essential here. So when Kennedy proposed Project Apollo, the U.S. had 15 minutes of human spaceflight experience. A lot of new capabilities had to be developed, new technology had to be developed, and this required drawing on a contractor workforce and also hardware that was also available. So at the time of the announcement, there was concern that there might be pathogenic life on the moon. There was this concern about basically a modern version of the Columbian Exchange, that the astronauts would bring something to Earth that could threaten life on Earth. And so they had to come up with a solution. The Lunar Receiving Lab was developed in order to allow lunar material to be studied in isolation, but there had to be a way to get the astronauts from their spacecraft to the Lunar Receiving Lab without contaminating the rest of the Earth. So this is where the MQF comes in. And NASA chose the company Melpar as a contractor. They're based in Fairfax County, so not very far from here. And they worked with Airstream, and they got this basically off-the-shelf trailer, and then they modified it. So this would minimize production and costs. It was small enough already to fit inside an airplane for transport. It's just 32 feet long, and it was already equipped with beds and a kitchen and a living room. So the modifications they made, they sealed the body of the Airstream so that it was airtight, and they added commercially available exhaust fans and filters to establish internal negative pressure, and they installed decontamination transfer locks to pass material in and out of the trailer, and they added some airline seats for when it was loaded on the airplane. But what's also important is what they didn't change. So they didn't change much of the living room, the sleeping compartment, or the kitchen. And I encourage you to visit this specific one out at the Udvar-Hazy Center near Dulles Airport, and you can look inside for yourself and see that it looks like an Airstream trailer from this period. 4 were made in total, and at a total cost of $250,000. The work began in June 1967, just 2 years before the first lunar landing. And this unit in particular was delivered at the end of June 1969, less than a month before the Apollo 11 mission. So it was very important that they were able to use this off-the-shelf product and to modify it to meet the timeline, and also to keep the budget within reason. And the astronauts landed in the Pacific. They were transferred to this mobile quarantine facility. They spoke with President Nixon, and then were transferred to the Lunar Receiving Lab in Houston. But instead of going into too much detail, and I'd be happy to do that later, I'll just say that this artifact and this larger story tells us about the limited knowledge of the moon when Project Apollo was proposed. It puts the audaciousness of Kennedy's proposal into even more perspective. It reminds us of the human scale of the program, of the challenges of being an astronaut, the risks they undertook, and then also of the quick timeline and the culture of innovation and problem solving that it fostered, the need for off-the-shelf solutions, and the key role of industry in making Project Apollo a reality within this short timeline. So I'll end my comments there and pass it on to you.
Thank you. So when I was in college, I didn't know what I wanted to do for a living, and John F. Kennedy made his "We Choose to Go to the Moon" speech, and that's what convinced me to become part of Kennedy's Children, as they called them at the time. And I got my advanced degree in aerospace engineering. I specialized in high-speed aerodynamics, which talks about guided missiles coming through the atmosphere if you're going after somebody. It talks about the flight dynamics of an asteroid entering the atmosphere. But it also talks about the dynamics of the command module returning from the moon and re-entering the atmosphere, and how do you go about flying such a thing to make sure it comes, it first of all makes it successfully and then lands hopefully near the recovery ship. I was hired by a company by the name at that time of TRW Systems Group, and they now do mostly auto parts and tires, but back in those days they were one of many, many corporations that were invested in helping with the Apollo program. I was in a group of about 100 engineers. We were located, our office location was directly across the street from NASA at what called then the Manned Spacecraft Center in Houston. And what we were 100 engineers that were supplementing the dozen or so engineers who had responsibility for planning, supporting, and training and supporting those flights. And so, for example, in my case, because of my background, I was assigned to reentry. So from the time the spacecraft comes back to the moon, touches the atmosphere until it lands, that was my area. But we had, those 100 engineers covered all elements of that plan, from launch through lunar insertion, to landing on the moon, to all the work that had to be done there, from returning from the moon, and then coming back to Earth. All of that was done by us. And in fact, in the case of both Apollo 11 and later for Apollo 13, we were also in those back rooms. So if you see the Mission Control Center of those days, and you see all the folks on mission control that are talking to people, the people they're talking to are in back rooms behind those screens. And I was there for those 2 flights because both of those were pretty critical. One because it was the first one, and the other one because it was unheard of. And so everybody had to be in there. And I mention that because what had happened with NASA before I got there, about 1967, was the Apollo 1 fire that killed 3 astronauts on the launch pad. It was Gus Grissom, Ed White, and Roger Chaffee, I think, were the 3 astronauts. And this was the first death during training, or during actually simulated a mission, that had ever happened to NASA, and it rocked them to the core. They moved back their schedule for about 1.5 years, trying to figure out what was going on, how that happened, how we could never let that happen again. That's when the failure is not an option culture entered NASA, because they were determined never, ever, ever to let this thing happen again. So when I got there in 1968, my first day on the job was October 1968. We had just gone back to space flight, manned space flight. So Apollo 7, I think, was actually circling overhead as I was looking for the bathroom. And the culture that NASA asked us all to do is to wear one badge, and that was NASA. We're not going to fuss with each other. We're not coming over here to talk about did Grumman cause this. That was not going to happen. Here, we're here to solve problems. We've all got a NASA badge. That's all we care about. And while we do this, we are NASA. And you answer to us and nobody else. And no infighting. Let's go solve the problems. That was the culture that I walked into. And it changed my life and my career forever. Thinking at that time that was the norm between government and contractors. But it did change forever the way I viewed that world, and it's a reflection of what NASA did, even with slide rules and without pocket calculators, to use 400,000 people as an extended team to make sure this thing was a success. And most of us didn't know each other. I mean, those of us on our program did. I knew the folks that were doing, other people at TRW, but there were people out there in recovery ships, there were people up at MIT, there were people in other corporate, and we're not exchanging email. We're not texting each other to see. I don't even know their faces until I saw movies much later. But we trusted them. They had to do their part as thoroughly as we did in order to make it work. And NASA was on what they came to call a fail-ops, fail-safe process, which says if something happens to this, one failure, we can still perform the operation. The second failure, then we have to have a way to bring them home. And everything was structured that way, so that if there was a problem, it was, number one, our job to go figure out how to fix it. But number two, that one problem should not cause the loss of the mission. We need to have a backup way to do it. And the second one need to be, and that second one may be human interaction, but the second one then had to be able to bring them safely. That was a culture that was foreign to me. I had never worked next to a government contractor before, as a government contractor directly with the government. And it was profound, absolutely profound.
Thank you. And thanks to Steve for organizing this event, sort of hatched at a dinner at a industrial automation conference in March. And I'm good at having ideas and then getting other people to organize behind it. So Steve's done all the heavy lifting to get everybody here, and it's a great moment. Like many people in this room, I have my own story of being inspired by Apollo as a little kid, which is not all that special other than watching it on TV and then, consuming books about it when I was a little kid. One particularly I wanted to bring here today, but it's actually too valuable, and it's called Apollo Expeditions to the Moon. It's a government printing office book, It used to be impossible to get. Now on eBay you can get it pretty easily. And it's a big format book, and it's just got all these great pictures with captions. And I don't have the original one I had. I got it on eBay maybe 10 or 15 years ago, and then since then I've got it signed by I think everyone alive who walked on the moon, thanks to our friend Larry McGlynn and many of the engineers. And so I actually didn't feel comfortable traveling with it. But it's amazing to go back through it, and I can still tell you the captions for these pictures. And I obviously had a big impact on my decision to become an engineer. I worked in underwater robotics for many years. Then in 1999, I just finished a book that was based on my dissertation about the history of feedback control and control systems in World War II. But it became clear as I was finishing that book that the real end of the story was the Apollo 11 landing. That was really the culmination of what Norbert Wiener called cybernetics, although it was much more than that, that had started in the First World War, actually. But nobody was going to want to read my book if I added 300 more pages to it. And so I started looking at the Apollo computer, which had been made at MIT. And it was one of those topics at the time where it was right around the 30th anniversary of Apollo. Everyone sort of thought they knew everything about it, and it really wasn't that interesting. And that clearly been demonstrated to be not true. And Teasel, the work she mentioned, and much of the other work she's doing shows you that there's still just a great deal of historical discovery about why Apollo is interesting. So I began working on this book, and it also became clear that it was just an amazing case study about how big engineering gets done. And most of the time big engineering projects get done, they're done within private industry, and they're not recorded and they're not publicly accessible. Whereas even if you're not interested in space flight, Apollo is the largest program that you can actually go get all the papers about and actually find out about. And so I began, actually was halfway through the book and I was stuck on how to finish it. And so I started teaching this class at MIT, Engineering Apollo. It's called Engineering Apollo, the Moon Project as a Complex System. It's a graduate class in aerospace engineering, and it's for engineers. And it's about how a project gets done. Technically, details of the control systems and propulsion, but also politically, engineering-wise, managerially. When he was alive, Bob Siemens used to come in and he would talk about briefing JFK in May of '61 about whether he could make this bold decision. And I started noticing of the astronauts who graduated from MIT, I'm going to forget the exact numbers, but it's basically like a third of the moonwalkers had MIT degrees. With the exception of Buzz Aldrin, nobody had ever invited them back to talk to students at MIT before. And so just that first semester, we had Charlie Duke, we had Buzz, we had Ed Mitchell, you know, and they had these amazing points of view. And they'd spent so many years talking to Rotary clubs. They were thrilled to talk to grad students in engineering, right? Because they could really talk about it in the terms that they had understood it. And then more and more we just found flight controller Cy Liebergott, and who you must have known, and many, many others. And obviously the industrial part of Apollo was a huge component to that. We looked a lot at the LOR decision, which among other things, when you decided to do Lunar Rendezvous, it meant that North American wasn't going to build the lander anymore. And there were industrial politics around picking another contractor. It turned out to be Grumman, of course. And so that course, I taught it for 10 years or so. Teasel took the course as a student, and I think you probably TA'd it at one point as well. I got to say, nothing gives me as a teacher more satisfaction than to see Teasel not only here, but at the Air and Space Museum doing what she's doing, because, you know, as she was coming through grad school, she had an interest in space and an interest in museums. And it was like, there's really one job for you, Teasel. It's that job. And I think when you were hired, it wasn't even quite the Apollo curator, but it became that way. And so it's just enormously gratifying to see Teasel and her work, seeing that broader audience at this moment. And there's an event at George Washington University, which Teasel was too modest to pitch, but which she's moderating with John Logston and Ellen Stofan and Mike Collins and Charlie Bolden, which really is the broad, I mean, it's a full auditorium of Teasel's graduate work on the diplomatic nature of Apollo and the tours that the astronauts took around the world. And I encourage you to go, although I think it's probably sold out by now. Just, you know, one but very gratifying example of how there's just, as a historical topic, it's just so rich, and there's still a lot of room for people to bring new points of view. On the subject of industry, I actually went up, and I apologize for not projecting them, but you can find these pictures just by Googling Apollo Prime contractors. And I think it's a small enough audience you can see. This is an image from the Brooks and Grimwood book called Apollo, Chariots for Apollo. It's about the Apollo spacecraft. And it's not even about the booster and the Saturn rocket. It's just the spacecraft, and it's listing all the contractors that made the spacecraft. And you can read down it. I actually suspect that most of them are still around. They've been absorbed and renamed, but I bet you if you looked, very few of them have gone out of business. Lockheed made the pitch motor. North American, of course, made many different pieces of the command module. Aeronica, Pratt & Whitney, Hamilton Standard, Rocketdyne, Thiokol, Northrop, now Northrop Grumman, Aerojet, Bell Aerospace, Honeywell, Collins Radio, Link Beach Aircraft, makes the airplane I fly, Bell, Allison, RCA, Westinghouse, Raytheon has been mentioned already. And actually, interestingly, they don't list here Ryan Aeronautical, who made the landing radar for the lunar module, who had made the Spirit of St. Louis. And, you know, just an amazing panoply of what American industry looked like at the time. And then there's a companion image, which is a map of the US with all those companies laid out across the US. So, you know, if there's one thing I want to leave you with today, when you see those pictures of the whole stack, because you could make the same diagram of the Apollo, of the Saturn stack as well, don't just see a rocket, right? See the map of US industry coming together to make that artifact. And that's really the kind of systems view of Apollo. And that's only the flight vehicle, of course. There's equally amount for all the computers and control systems on the ground. And you know, one of the principles of the Cold War space race was really that progress in human spaceflight represents progress in the civilization, right? It turns out, I think we know that to be not really true, because the Soviets were doing great at human spaceflight right up to the moment that they imploded as a civilization. But in this case, the strength of Apollo really was the strength of American industry, laid right out upon the map of the US. North American is a really interesting example there. And, you know, they had made the P-51 Mustang, arguably one of the airplanes that won World War II. They had made the F-100, a Cold War Century Series fighter. They had made the X-15, which a lot of the Apollo control system and shuttle control systems were based on. And then they made the spacecraft. And, you know, interestingly enough, North American actually drew on a lot of the work that had been done at Bell Labs around frequency domain controls and for telecom and radar systems, which became the basis of cybernetics. Applied those to aerospace systems, and you can actually find, it's another great diagram. There is a frequency domain diagram of the vibration modes of the Saturn stack. And it's an amazing, it's like mapping the Saturn stack as a radio station, really. And that's how you had to do in order to fly something that big. So MIT built the Apollo guidance computer. It was the only one of that list of primes that was not a private company, that was a university. And Bob Siemens was very clear, because I asked him this directly before he died. Was that because the president was from Massachusetts? And he said, yes. But also it was because navigation was considered extremely hard, and it was really, very much to the credit of the early Apollo architects. They realized that was one of the most uncertain pieces of it. The F1 engine was already running. You kind of had a Saturn. Kennedy wouldn't have made his announcement without that. The navigation part was still quite uncertain. It was the first contract let in all of Apollo, was the Apollo guidance computer contract let to MIT. The speech was in May 25th, and the guidance computer contract was the end of July. I mean, when does anything happen that fast? And there was a great deal of industry protest about it because it was felt to be anti-competitive and anti-commercial, and letters to congressmen. Unfortunately, it was actually legal, so the grant stood. But even then, MIT subbed out anything that was remotely looked like manufacturing to AC spark plug. I love the fact that the gimbals on the spacecraft were made by a company with spark plugs in its name. Colesman Optical, and as was mentioned, Raytheon really manufactured the computer. So one of the things I think that's so interesting about this week is the ways that we're seeing, people used to talk about Tang and Velcro as the spin-offs from Apollo. Now we realize it was a much deeper, much subtler impact that maybe even took 30 years to really find its way out there. Of course, the private space flight, the clearest examples are Musk and Bezos, are being funded not by people who went on to do aerospace innovation, but who were inspired by Apollo and went into the computer world and made their fortunes and then are coming back. And there are countless numbers of people who did that. I'll give you my one personal example. John Pilko now teaches the Engineering Apollo course at MIT because I've been on leave for a few years to start my company, which is how I know Steve, called Humatics. And one of the first things I did when I started the company is I went and talked to Dave Scott, who was the commander of Apollo 15, and an MIT graduate who worked on the Apollo computer, and recruited him as our founding scientific advisor. And by the way, 2/3 of our company is in Waltham, Massachusetts, and 1/3 of it's in Huntsville, Alabama. And there are people in Huntsville who are children of people who worked on the Apollo program, who are now electrical engineers working in robotics. And Dave very generously agreed to be one of our founding advisors, along with my mentor in the underwater world, Bob Ballard, and incredibly effective tool at recruiting people to feel like we're working in that tradition, and the tradition of Massachusetts and Alabama working together that got us to the moon. And by the way, we just, about 6 months ago, moved to a new facility in Waltham, Massachusetts. We are next door to the place where the Apollo computer was made. And it's not a coincidence it was in Waltham, Massachusetts. Waltham is United States' second oldest manufacturing company. And it was a textile town before it was a precision manufacturing town. And as was mentioned, the code for the Apollo system was literally woven into magnetic cores by then unemployed and then reemployed textile workers. So Raytheon itself was drawing on the industrial history of the US, literally in these old textile mills, to weave the software for this incredible program. And Neil Armstrong and Buzz Aldrin would go tour those factories and kind of personalize that story. So there are these many subtle and probably the most important ways that Apollo, and again, the part I've always focused on is the digital part. It really was the first time that a computer found its way into something other than a big air-conditioned building, especially one that had people's lives on it. And who can count the number of times in the following couple years, of course the microprocessor was invented the year after Apollo 11 landed, that an engineer would go to their manager somewhere and say, I want to put a microprocessor in this thing. My father did it. He was the first person to put microprocessors in film strip projectors. And the manager would say, why would I take that crazy new thing and put it in, this important product for ours? And the engineer would say, well, NASA just did it for the lunar module and the command modules to land on the moon. It's probably it's been reliable enough there. You'd think it's reliable enough for our slide projector or our dishwasher or our industrial controller or that. And those things are very hard to measure, and they're very hard, and nobody's actually even tried to do that research to measure that impact. But I would argue that that's the biggest industrial impact of the Apollo program. Slow, subtle, invisible, but 50 years later, in some ways, the most important. So I'll turn it over to John.
Okay, I'll try to add to all of those comments. I also grew up during the Apollo era, started writing handwritten letters to NASA, and I ran out of NASA centers to write to. I upgraded to a typewriter, and eventually I convinced my father to buy an IBM Selectric used typewriter from the IBM reuse store, and now I'd start getting boxes of material, and I started writing to each of the contractors who worked on Apollo, who every letter got responded to, and usually with boxes of technical documents that related to how this program worked. One of those was the MIT Instrumentation Lab. I just thought it was a computer company. I had no idea there was a university attached. So it's kind of come full circle in that regard. Just to comment and kind of add to what made this possible, I would start with the word mobilization. This was a massive mobilization, really at the scale of World War II. In fact, much of Apollo is kind of is an echo of World War II. The geopolitical domain that Kennedy faced was effectively set at the end of World War II, the beginning of the Cold War. Most of the people that had worked in this field had the experience of either working during World War II in industry, serving in the military, or working in labs. A good example is Charles Stark Draper. We talked about the role of rapidly awarding the contract to the instrumentation lab. That was made possible by a couple of key relationships. One is that James Webb, the administrator of NASA, had served on the board of directors of Sperry, who had produced the Mark 14 gun sight that Draper had designed. 85,000 of those were built in World War II. It was critical to the Navy being able to defend ships from, mostly in the Pacific, from aircraft attacks. But that reputation that Draper had was well known to James Webb. Bob Siemens was Doc Draper's PhD student and had worked from 1941 to the early 50s at MIT, leading one of the major missile development programs called Project Meteor, which was done for the Navy Ordnance Division. So these people had experience coming to the program. They knew the key relationships had already been built. Some of them were rivals, I think.
And Siemens was a Harvard classmate of JFK.
Right, from the class of 1941, more of an acquaintance, but now, you know, when this all came together, the NASA headquarters was at the Dolly Madison House. You can still go see it. It's on Lafayette Park, 1 block from the White House. In those days, NASA had a very, very small staff. And what they really did is rapid response to the geopolitical opportunity that was presented when Kennedy was ready to consider this goal. And that's really only a period of about 6 to 8 weeks, depending on how you count. In fact, they had a meeting with Kennedy to discuss a increase of the NASA budget, where NASA had proposed numbers on the order of $150 million to accelerate the Saturn V. This meeting was held in March. Kennedy cut the numbers in half in March of 1961. But the events of the failed Bay of Pigs invasion and the Soviet success with the Gagarin flight really propelled the urgency. And Kennedy asked for a redo of his joint speech to the Congress, which is highly unusual. A second State of the Union message. He had the inauguration, the first State of the Union message, and in May of 61, at a second joint session of Congress to sort of restart his presidency, proposed the lunar landing goal as a way to do that. That came together because people like Siemens and Webb and George Low and the people that were planning for Apollo could respond rapidly to a president when they made that, when the political window was effectively open. And I think that same rapidity applied to the way the contracts were developed and released. A good example is the lunar module contract to Grumman. The lunar orbit rendezvous decision was made in July of '62, announced to the public. NASA rapidly ran a competition for that. The proposals came in roughly September of '62, and the award to Grumman was made in November of '62. Now, behind the scenes, there was still dispute over whether LOR would actually be the right decision. It was opposed by Jerome Wiesner, who was President Kennedy's science advisor, and he was gathering the momentum internally to try to derail it, including addressing arguing in front of the press on a trip that Kennedy made to Huntsville, actually, in September of '62. NASA moved so rapidly that Wiesner's arguments could not really reach Kennedy. In fact, the pivotal part of the time when Wiesner maybe would have had a shot at turning this around was in October, when the Cuban Missile Crisis took place. So Kennedy was otherwise occupied, and NASA had the LEM under contract before Wiesner could actually gather the forces to argue why LOR was not the right choice. Now, throughout that period, there were challenges. There were programs that had to be replaced or supplemented. A good example is the lunar module ascent engine, which is a critical piece of the propulsion to get the astronauts off the moon. That had originally been awarded to Bell Aerospace in Buffalo. It was a derivative of the Agena engine, which Lockheed built for the Corona program. That program got into trouble in terms of being behind schedule. It had combustion and stability problems. They brought in Rocketdyne, which is effectively a competitor, to help solve the combustion and stability problems related to that engine. And that was not the only case. There were many cases where NASA oversight of the contractor base was really essential. In many of these situations, NASA acted as the prime integrator. There was no systems integrator, as we know today. NASA was the integrator. But besides the direct relationship with the contractor, they would often reach down into the subcontractors, and a good example of that is Link Aviation in Binghamton, New York, which built the Apollo mission simulator and the lunar module simulator for the Apollo program. They had Grumman as the prime on the LEM had picked Link, and North American Aviation as the prime on the command module had picked Link as well. But to assure that that program succeeded, NASA got involved in a very aggressive oversight program to manage Link. And effectively, as the program proceeded, particularly in the mid to late '60s, the Link people were responding to NASA directly as opposed to North American and to Grumman. One thing I'd like to point out is the sort of three cultures of NASA that came together to make Apollo succeed, what I call the three strands of DNA. The first is the team under Robert Gilruth that came out of Langley. Langley was a 40-year-old NASA facility, previously the National Advisory Committee for Aeronautics, NACA, NACA. And that entity was a startup. Gilruth was given the responsibility to build a team. There's a letter in the NASA History Office dating back to October of 1958 to the new administrator of NASA, Keith Glennon, basically where he's given authority to run Project Mercury, and he asked for 38 people. I think it's 25 engineers and some administrative people that became the core nucleus of the Space Task Group, and they functioned as a startup. They were a startup within a government enterprise. Similarly, in industry, these companies were young companies that functioned largely with entrepreneurs in charge, running these programs as in sort of a startup atmosphere. A great example of that is James S. McDonald at McDonald Aircraft, which was picked in 1958 to build Mercury. That company was 19 years old. It was founded in 1939. It had grown through the World War II, but was really being driven by a hands-on entrepreneur, James S. McDonald. Very similar parallels to SpaceX today, which happens to be about 18 years old, driven by an entrepreneur. These were not sort of uncommon. Today we look at the large aerospace companies as sort of monolithic enterprises, and in reality they were all started with entrepreneurs, and in this era, particularly the 50s and 60s, the entrepreneurs were still running those companies for the most part. So the second strand of DNA is the von Braun team, and they had a completely different approach, which was an arsenal-based approach that they had developed at Peenemünde, brought to the United States. They had worked together for, in some cases, over 25 years at the start of the space race. Very different. They needed to bring projects under their control. One of von Braun's first moves was to bring a machine shop from Atlanta to Huntsville because there wasn't a machine shop in Huntsville. They brought IBM Federal Systems Division into Huntsville to build the instrument unit for the Saturn V so it could be under their direct control. Melding these cultures was very challenging, and this was a primary role of NASA headquarters. I would say fundamental to the success is the third strand of DNA, which was the systems engineering groups that were brought in to manage that expertise, mostly from the Air Force ICBM programs, and the key players there were people like George Miller, Sam Phillips, Joe Shea, and these were systems people with extensive experience on programs like Polaris and Minuteman and Atlas, and they were basically able to sort of blend these cultures, get the Gilruth culture that became the Manned Spacecraft Center in Houston to work with the culture on the von Braun team, but also to manage this broad array of contractors and subcontractors across the United States, which was a massive challenge. As Teasel points out, the contractor base grew by a factor of 10 between 1960 and 1965, and it was an exceedingly challenging domain. And I think one of the big differences is there was trust between the teams. They had high levels of experience and high levels of trust. When NASA won the Apollo, when NASA was picked to do Apollo, they had 3 lawyers. Today, there are 300 lawyers at NASA. The proposal for the instrumentation, for the MIT Instrumentation Lab was 75 pages. It has 1 graphic, which is a figure-8 loop of Earth, Moon. It's hand-drawn. You know, today that would be 7,500 pages. It would have hundreds of graphics. The proposal itself would take, you know, 6 months to write. It would take another 6 months to review. When the contract was announced, it would be likely protested. That really didn't happen in those days. There were protests, as David pointed out. Congressmen were not happy that MIT was picked sole source to do the Apollo guidance computer, but NASA managed all of that, and particularly the political side, to get the Congress to provide the funding, and particularly James Webb had that responsibility. So those are kind of my overall points that I'd like to add.
Great, thank you. So now we'll have a bit of a discussion and then open it up to question and answer. But to start off, could you all comment on how Apollo was organized and what role industry had in that organization?
I think we've sort of covered that one, actually, John, especially.
So what were some of the challenges with that organization, that approach to doing Apollo?
So, you know, the Apollo 1 fire was one of the places where these cultural conflicts really boiled over. And again, North American, at some way, the way I described it, you can look back of it as one of the industrial heroes of the program, but they were also they felt they were the scapegoat. They were blamed for the Apollo 1 fire, and the congressional hearings were very damning to the way they were approaching the spacecraft, which they objected to. They felt they were treated unfairly, and that they were misrepresented in those hearings. But that was a place where this clash of the three cultures came to crisis. And actually the systems guys were out. And it was really the rise of the kind of the Space Task Group, which Houston was the Space Task Group from Langley, basically transplanted to Texas. And the rise of the flight directors and flight control, and Houston as the real center of the program, which was much more based on a kind of the older Langley test pilot flight test culture, as opposed to the more West Coast ICBM systems engineering culture. And you know, Shea quit, Siemens stepped down not too long thereafter, and you know, again, I'm reminded of this every day because my startup is always in this mode. But you know, up until July 20th, 1969, the whole thing was a big mess, and people were just trying to get there, and there was a tremendous amount of uncertainty. And it's amazing that it worked at all, like any human enterprise. There was conflict, there was delay, there were accidents, there were fatalities. You know, the story wasn't written until it was written, and in that there was all of this difficulty.
So I think the term that was used was that NASA became the systems engineering arm, and that's true. Mm-hmm. And so they then became the glue that pulled it all together. That culture that they infused pulled it all together. There were problems on every flight. Some of them not too many people know a lot about. Some people do know about Apollo 13, but every flight. Some of them could have been very disastrous. But what saved them wasn't the technology. It was the teamwork. It was the failure's not an option. It was, what are we going to do about getting out of this? How do we fix this? Their whole progress, although quick, took, with the exception of Apollo 8, took them through all the steps required to land on the moon, from taking the Apollo spacecraft up first into orbit, then what would have been Apollo 8, that was Apollo 7. Apollo 8 would have been the next step on that. That's where we got jittery and decided to go to the moon first. But Apollo 9 then took the lunar module into Earth orbit, and they tested it there, and they separated and came back together. Apollo 10 took the whole system up to the moon and did a complete dress rehearsal short of landing on the moon. And in fact, there were some surprising problems with that. And I've said on other occasions, had I been the commander of that, I might have said, something looks funny to me here. I'm sorry, Neil, I'm just going to have to drop down. You know, because they were there. They had done it all but land. But that whole process was to test those procedures step by step by step by step. And then even if Apollo 11, for what reason, was aborted, Apollo 12 was scheduled for November, so that we could still have John F. Kennedy's command to get this done by the end of the century fulfilled. So that's what Apollo 12 was for. So that it was done procedurally with 400,000 people and a lot of trust, and NASA playing the system integrator with a culture that came out of them knowing personally and closely those 3 astronauts that died, and they weren't going to let that happen again. That was really key to it.
So let's bring that story forward a little bit and look at what happened in the 1970s and the 80s and 90s into today, and how has the role of industry and its relationship to NASA changed over that period of time?
One thing that's worth mentioning too is that James Webb, who was also in some ways a casualty of the Apollo 1 fire, he left NASA in '68, I think, and was not the administrator for the great landing. And he went out and started an industrial consulting practice, saying, NASA solved all these problems, NASA learned systems engineering so well, let's apply that to all this other stuff in the world. And it was not successful. And urban problems were much more difficult and more complex in some ways. And so as we think about the legacy of Apollo, there were some of these shorter term attempts to diffuse it that maybe in retrospect they were premature, that it was a very different path for Apollo's lessons to find their way into industry. It's also worth, and maybe John can say more about this, remembering that the key decisions on the shuttle, which were then baked in and a lot of the source of its problems over the coming decades, were made by the Apollo leadership during the Apollo era. And so it's very hard to think of Apollo and Shuttle as these two separate eras. They were really mirrors in some ways of the same team.
I think for the most part, NASA has been under-resourced relative to human spaceflight since Apollo, and you really look at the shuttle decision, it was heavily influenced by OMB. So in the case of the Kennedy decision, Kennedy was very involved. It was he constantly questioned the decision and even thought about cooperative efforts with the Soviets. In fact, just before his death, he spoke at the United Nations proposing a joint flight with the Soviets. Nixon was very different. If it was related to diplomacy and international relations, he was interested. He promoted the idea of flying even an international astronaut on one of the later Apollo missions. That never got momentum, but then suggested the role of international participants on shuttle, the role that the Canadians and Europeans would have on the robotics for the shuttle arm and the space lab. But for the most part, the decision around the shuttle was really left to OMB. In fact, the most critical memo on the shuttle program is from Cap Weinberger, who was the deputy director of OMB, to President Nixon in, I think, August of 1971, that basically rationalizes the decision to do the space shuttle program on the basis of national pride and sort of technological image that the world would recognize. The one response from Nixon is, "I agree with Cap." That's sort of the definitive memo that created the shuttle program, later announced in January of 1972. NASA in shuttle starts to really look at the lessons of Apollo and how to do things differently. And a good example is the software, the guidance computer, a very different approach that they took. I think they were very dependent on MIT for all of that activity, and in the case of shuttle, they started to change the approach. They went to IBM, Federal Systems, and Owego for the AP101s, the 5 computers that would run the shuttle. Another group that had spun out of MIT, Intermetrics, was a key player on doing the software for that. Draper continued to have a role. Honeywell was involved. And NASA served more as a sort of oversight of the actual flight controls and the software. A good example is the head of avionics and Cy Rubenstein, who became the shuttle program manager out at North American, wanted the hardware in the loop simulator to be at Downey. And NASA wanted it in Houston, and they prevailed. What was the what became the Shuttle Avionics Integration Lab, the SAIL, and so NASA had control. All the software that had to be developed in the future that would run on the space shuttle computers was tested and validated in the SAIL before it was put onto the orbiter and flown. So. There were changes made in that whole structure of the way NASA dealt with its key contractors. As to the way the industry changed, that's a much broader question. I think there are a lot of parallels. The whole process of concept design review, preliminary design review, PDR, CDR, all of those approaches to program management are very much the same. Almost every government program today in industry, whether it's a large company like Lockheed Martin or Boeing, or a small company like Aurora, we follow that process very, very religiously. And it's really the combination of the NASA approach with the combination of the systems approach that was used in the ballistic missile programs that created that approach for program management. The industry is very different today, as I pointed out earlier. Lawyers are much more involved. There are fewer handshake type approaches. Kelly Johnson could write a proposal that was a few pages long and get a handshake from his customer to do things like the U-2 and the SR-71. Can't do that today.
Yeah, Jack.
So I work on Apollo from 1968 to 1974, and then TRWS Systems lost a contract bid to do something for Space Shuttle. And a number of engineers, about 50 of us, moved literally down the street to IBM, which was, their offices were directly across the street from the Space Center. And we were there because IBM had won the contract there to develop and test and support all the flight software to be used on board the Space Shuttle for all the shuttle missions. And so the engineers were there because NASA didn't speak programmers and programmers didn't speak NASA. And so they decided to bring in a group of engineers to sort of be the translators. And so our role was to work with NASA and for the requirement stages and say, okay, what do you need here? And then go back and work with the programming team and figure out how do we make that happen and how do we make it fit in the computer and run in enough cycles and so on. And here again, that same NASA culture was in place. I was dealing with directly, in fact, my customer was John Aaron, who managed all of that for Shuttle. He was a flight controller on Apollo. In fact, he saved a couple of missions. But he had moved over now, and he's responsible for managing the software quality and the software production, again, as sort of the lead system engineer. And an interesting thing to me is when I left TRW, we had one woman on the team that was, she wasn't degreed as an engineer, but she was an engineer. She was the only woman from TRW at that time who actually was in the control room supporting Apollo 8. And the rest of it was kind of an all-male culture and slide rules. So now I go down to, and this is 1974, I'm going down to to IBM, and virtually the whole team is women. Because I wasn't taught programming when I was in college. A lot of engineers weren't. We used the computers, but we didn't do programming. That came out of the mass, just like in the movie Hidden Figures in the 50s, if you saw that. When that started, that continued to evolve, and there was another generation of women who had gotten degrees in math and applied to support the development of these, except now they had real computers and real software. And those computers are going to run everything. So on Apollo, there was so much backup work, and you had to be careful that the onboard computer worked. On Shuttle, you're launching this thing vertically, and it looks like an airplane. And those engines, to keep it from toppling over, are just hunting all the time as it goes up to keep it stable, like balancing a broom on your finger. A human can't control that. A human could not fly an asset. And so not only did the software do it all, but it actually kept the astronauts from making mistakes. So it would override some of those decisions that they would make because it had to be managed. And that transformation occurred just in those few years. And we were using computers by that time. So although the astronauts could do a lot of things manually, and they did a lot manually when they were in orbit, and they do when they were working to retrieve or to put out spacecraft or whatever. During reentry, the same thing happened. During reentry, there was times during that reentry where the pressures on that thing and the way it wobbled around could get you in a lot of trouble if you grabbed that stick. And so the computers were running that one too and overriding the astronauts if they tried to. And think about the difference in just those few years in the technology, in the role of the software, and frankly, in the entrance of women into I mean, when I left that, I ended up running that organization until about 1984. And when I left, when I got there were women in management team, already managers and leaders. When I left, a woman replaced me in that whole job, managing the whole project. That whole thing happened basically overnight. And that technology and that culture. And then what happened was a lot of the old hats from NASA started retiring. The people that had gone through all of Apollo and all of Shuttle were going on to other things. And any culture has a half-life. Any culture has a half-life. And so it's hard to maintain that same culture when people move on and that reason to have that sort of culture stays. And that's happened with every entity, but it also, you began to see some of the cracks in this concrete after that group of people left. And new people came in to then start trying to get all these programs back to the level of Apollo.
So we've mentioned Tang and Velcro, which are actually pre-Apollo technologies. So instead, let's shift the focus to what are some of the... Sure.
Tang was not ever flown on any Apollo mission. Apollo, there's a book called Marketing the Apollo. NASA would not allow any public, I mean, any promotion of any vehicle, anything, including Tang, to be spoken by those astronauts, to do any of that kind of stuff. They think they had something that was sort of like Tang, but they were not allowed to say so. So Tang just declared this is, and NASA wouldn't confirm or deny it. So, so we don't know about Tang.
Yeah. So we'll also shift the emphasis away from Tang and instead look at other technologies, products, or business practices that emerged from Apollo that have formed a bedrock of the aerospace industry.
The best examples is digital fly-by-wire. So the Apollo spacecraft was flown through the computer. Both the command module and lunar module were digital fly-by-wire systems. They were the first of any flight vehicle. In fact, the team that worked on that at the instrumentation lab in the fall of '64, they were taking the first course taught at MIT in optimal control theory by Michael Athens, and then going back into the lab and programming it into the Apollo guidance computer. With the success of Apollo, a team out at the high-speed flight station, NASA Dryden, came to headquarters and met with the new NASA Associate Administrator for Aeronautics by the name of Neil Armstrong. This is the position he held at NASA after Apollo 11. And they basically said, we want to do a digital fly-by-wire in an aircraft, but we think we're going to have to build a computer to do that. And he basically said, well, I think I know of one that already exists. I just flew it to the moon and back. Go see these guys up in Cambridge. And basically the team took an Apollo guidance computer, actually from the Apollo 15 mission, the actual one, and put it into an F-8 aircraft, Crusader, out at NASA Dryden, and conducted the first digital fly-by-wire demonstration in roughly 1971, 1972. That continued to evolve. In fact, for the space shuttle, that system was ultimately upgraded to use the 5 AP-101s, and when they had a pilot-induced oscillation on the 5th approach and landing test, which is pretty serious on the Enterprise, NASA then used the F-8 with the AP-101s to basically validate the patch to the control laws that would solve that problem. So that lineage permeated the entire industry. Almost every military and commercial aircraft today uses digital fly-by-wire, and it's really one of the, I think, lasting legacies of Apollo.
That original F-8, it used 60% of the Apollo software to fly the airplane. That's how versatile that code was. You know, people forget also that the microprocessor was invented in 1970. Not an Apollo project per se, but the timing was very similar. And so by extension to the fly-by-wire story, Apollo was really, I always describe Apollo as the moment when people stopped bragging how big their computers were and started bragging how small they were. Which was not, you know, something that occurred to anybody really, except for maybe a few in niche aerospace applications in the 60s. And so instead of talking about the special air conditioner and its own fire department that your computer had, you would then talk about how small it was, which is so much a part of daily life today. And the notion of computers out in the world doing stuff, turning things on, turning things off, giving people information to get stuff done in the moment in their environment rather than a computer as numbers in, numbers out, you know, punch card stacks in a big computing facility, so characteristics of our world today, almost overwhelmingly so. You know, that's an Apollo thing. And would it have happened anyway? Probably. But would it have happened at that moment with that level of scale? You know, probably not. Moving from aircraft into desktop calculators and then into all kinds of other industrial equipment, the notion that a computer was something that could be with us. I think actually also Apollo is the moment when the measures of progress of the 20th century, which were basically faster, higher, further, and Apollo to this day is still fastest, highest, furthest that people have ever gone. 1969, 50 years ago, and changed. After 1970, the measures became very different kinds of things like processing cycles per second, or cost per passenger mile, or other measures of environmental emissions, or much more complicated, I think of them as socioeconomic or socio-technical variables. And I certainly talk to people in my book who were 50s and 60s aerospace engineers who are still horrified by that fact. You know, the airplane with the fastest, the world speed record still to this day was designed in 1958 or 1961, the SR-71. So the kind of raw Newtonian measure of technological progress of the 20th century really changed with Apollo toward a measure of these other kinds of information process kind of systems variables. And what I think is so interesting about Apollo is that it's the embodiment of that older way of seeing the measure of progress. And you know, the giantism of the 20th century, what could be better? It's sort of the ultimate giantism is the Saturn V. And yet it also contains within it the seeds of that new way. Actually love Norman Mailer's phrase for the command module was brain case on the tip of a firecracker. And it's a great description of that Saturn stack.
If I could just add, you know, today when you go to Silicon Valley and meet with the leading companies there, I frequently have been asked the question, why don't you aerospace companies follow Moore's law? And the reality is, Apollo is what drove Moore's law. When Gordon Moore published Moore's law in March of '65, the Apollo program was the only program he cited in that paper. And 2/3 of the production of Fairchild Semiconductor, the integrated, the microcircuits that went into the Apollo guidance computer, the integrated circuits, were based in that production period from 1962 to 1965 that Moore's law is based on. The other program being the Air Force Minuteman program. And that was a really bold decision. Eldon Hall was the designer of the Apollo guidance computer. Most of the focus had to be, were these circuits reliable enough to be used in the computer? They certainly would benefit on things like size, weight, and power, but would they be able to achieve the reliability that was needed to succeed? And the bottom line on that, and you'll appreciate this from a personal computer standpoint, not a single hardware failure in the entire Apollo program of the Apollo guidance computer. So they sort of proved themselves on that reliability, and much of the work that was done is really sort of manufacturing process technology. So you could make a strong argument that aerospace is what drove the creation of Silicon Valley, not what's lagging it.
So now we have an opportunity to open up questions, if there are any questions from the audience.
Yeah, I'm going to moderate these questions so that Teasel herself could participate in answering them. Please. This gentleman here will bring you a microphone. Please identify yourself. You know, I didn't mention, but certainly I'm obliged to do so, that this entire event almost obviously is public and on the record. And so please identify yourself before you ask your question.
My name is Lawrence Robinson. I'm retired from Rockwell Collins, formerly the Collins Radio Company, and thanks for the props, David. I'm sure you knew that I was going to hurl fruit at you if you didn't get that in. Thank you.
Like the director of the Collins Radio History?
I was
Museum?
the curator of the Little Company Museum in Cedar Rapids and co-founder of the Arthur A. Collins Legacy Association.
Welcome. Thank you for coming.
Yeah, thank you. This is just a wonderful presentation and enjoying it very much. I've read and seen a lot of discussion about how the roots of modern software engineering discipline can be traced back to the AGC gang at Draper. What I have not seen in similar vein is how does the modern discipline of systems engineering, not in the IT telecom sense, but in the NCOSE sense, and by the way, NCOSE was not established until 1990, how does that notion of systems engineering relate to the space program? And to me, it boggles the mind by today's standards, system of systems, Apollo is magnitude order beyond what we have today.
All right, let's, Jack, if you could start in on that. There's been mention made of how it's the system, the modern system protocol of just system engineering, but why don't you?
Systems engineering today is probably, in this largest sense, is probably unattainable. You have so many subsystems, and each of those subsystems that goes into like an air traffic control system, for example. If you asked FAA what their system is, it's the air traffic control system for the United States. If you ask the people who are developing the new code for it, it's this piece that runs on a computer for them. Each of those have to be managed like systems because they are no longer separate entities. There's no easy way today to put a system that could cause death, destruction, or a loss of a major project and have it kind of be insulated. Because anything that you lose down in there will pop up to catch you sometime later, and nobody knows about it because this was done in isolation. So today's systems engineers, to me, are really a spectrum of folks that, if it's a government contract, runs all the way back, hopefully at some point, to the customer themselves. And it's a much more difficult problem for anything large, like a spacecraft or like an aircraft or something, than it was, for example, even for Apollo, because the systems themselves were small and could be integrated, and then NASA also had the capacity to provide that role. Does that answer your question?
In terms of the disciplines of requirements management, traceability, how much of that can be traced back to the Apollo
I think, John, you alluded to that, how the whole protocol of program management anyway, and to some degree system integration, was defined then, and we do it still today. Is that right?
I think NASA was one of the first to fully document this and release it. The NASA Systems Engineering Handbook, which I think the first issue was published around 1970, is sort of still the basis of that entire discipline and that professional organization that you refer to.
In COSE.
In COSE. And I think you have to remember in these days that systems engineering, in my view, was always a truncation of the word control systems engineering. And so many of the people like Bob Siemens were really control systems engineers. They were also often viewed as chief engineers. Now today there's a sort of a dichotomy between a chief engineer and a systems engineer. But in this era, they're very similar, and today the systems engineers deal with these promulgation of requirements and deal with sort of the V-shaped famous chart, which I think is in that book. But in those days, I think the words system engineer and chief engineer were almost used similarly. And I know at Aurora, we kind of adopted that approach. Was Kelly Johnson a systems engineer or a chief engineer? I could make an argument on either case, but he was probably both. Now, the biggest difference is his requirements were much simpler, and I think that's the biggest difference in this era, that the requirements definition was maybe a 2-page document, not a 2,000-page document.
One of the interesting
David?
ironies of the space race actually was that the form of system engineering that NASA adopted for Apollo was very hierarchical and very top-down. And the form of engineering that occurred in the Soviet space program was actually very competitive and very distributed. and very much less centralized, which is the opposite of how the political systems like to think about themselves, right? NASA succeeded because it was, or Apollo succeeded because it was a very hierarchical project in a lot of ways. I think those two things are still very much in tension. Again, even within Apollo, the kind of space task group culture versus the systems engineering culture were in tension. Today, agile techniques, agile methods are still in tension. They're in tension within my own organization of 50 people about what's the quickest way and how do you get stuff done and how do you make it sustainable. And so those tensions haven't gone away. They're really fundamental systems architecture questions. The origins of systems engineering go back to the AT&T and Bell Labs in the 20s and 30s and electric power. And those cultures were both transported to the West Coast by Ramo and Wooldridge of TRW. I think I forget which ones exactly. They both had done time at AT&T and at GE, and many others like Mueller who became leader in Apollo. And so that older systems engineering was definitely incorporated in, although I think morphed during the 60s as well.
I think it's worth pointing out in this period, Bob Siemens went to the president of Bell Telephone Laboratories and asked him to create an entity that would provide systems engineering expertise to headquarters, and that was known as Bellcom. And Bellcom is the only organization in this group that actually had a sunset clause. When the Apollo program ended, the organization closed down, but Bellcom had, I think, upwards of 600 people supporting headquarters in all kinds of roles, but primarily for systems engineering roles, and they brought in that Bell culture that David referred to.
Jack, did you want to get in on this?
Quick thing. Another difference on Apollo and Space Shuttle both, the users were integral to that requirement. The Apollo astronauts, the Space Shuttle astronauts, they were directly part of the definition of those requirements. When we moved on to air traffic control, the users were consulted. Requirements were coming out of Washington, and then the users, which were out in the air traffic control centers, could be consulted and brought in for, kind of as a sidelight. And because of that, there started to be a canyon, actually, between what the requirements, we were fulfilling the requirements, but the users weren't happy with, right?
There's a question here from this gentleman. Please stand up and identify yourself.
Hi. Hello. Sorry. Tim Rideout. I'm a nerd from Massachusetts. So I appreciate all the MIT folks here. And I have a social science background with political science training. So, without getting into internecine warfare, we have to deal with consciousness and human motivation. So it's a harder discipline. In fact, you guys are part of what we study to be. So, anyways. And I occasionally burst bubbles also, but I only do it because I care. And so my broader question, and I'm supportive of all the space exploration. In fact, I'd love to be part of it. But when it comes to, if you think of all the humans involved as a complex system in building and maintaining and disciplining, team of teams, if you will, it seems that some of the captains of industry are currently malfunctioning. I'm talking about Elon Musk. I'm talking about Amazon. I'm talking about the lack of discipline at the top. And basically, if we're going to, you talk about risk aversion, and if we're going to trust that these people are actually, there's evidence for this. I'm not making this up. Elon Musk is smoking joints on television, and he has all these wild ideas that he never follows through on. And it's hard for the average person to trust. And I trust the Raytheons and the Lockheeds and those of the world, but I don't trust the newcomers. So basically, put differently, who are the generals of industry and the new Space Development Agency and all these people who are making these captains of industry fall in line, and because it requires a lot of discipline to do this.
I'm going to, you can answer that question, but I also
Sorry for being long-winded.
want to harken back to the point that was made here about how the industry that accomplished Apollo was that entrepreneurial industry of its age. And so I'd be interested, in addition to whatever response you may have to whether there are generals today on which we can have confidence, how different is the entrepreneurial culture of today as well it was in the early 60s? Jack?
I've been asked several times, is Elon Musk the new JFK, right? Can he inspire us to do all that? And my answer has been, Yes, but we never asked JFK to design the spacecraft. There's a space shuttle astronaut that made a comment, something like, space is hard, and particularly the first part of space, which is getting off the surface of the Earth and into orbit. And it doesn't really care about your ambitions. It doesn't care about whether you think you can or cannot get there in 3 years or 5 years. Things go boom, and space doesn't care. And so if you're not going to take that same approach, if you don't have that understanding, that fundamental understanding of what it takes to make these things happen, and for every, quote, anomaly that shows up, go dig through the dust and say, are there more of those hiding in there, and what the heck happened here? Because what's going to happen if we're not careful, if we're driven only by a political agenda, is a spacecraft's going to go boom, and we're going to lose people, because space doesn't care.
Are these entrepreneurs by culture or temperament somehow different than the ones in 1961, John?
I don't know. I would argue they're more common, and there are more similarities on the entrepreneurship side. I'm going to take your question in a slightly different direction, though, since you're a sociologist from Massachusetts. Probably the best book that was written by a sociologist about NASA was the Challenger launch decision by Diane Vaughan, and she published this book around 1992. She studied the NASA culture that led to Challenger and coined the term normalization of deviance, which is the basis effectively of both the loss of Challenger and the loss of Columbia. That the system had inherent failures that were being experienced. In the case of Challenger, the 25th flight of the shuttle, there had been damage to O-rings on every launch and some serious burn through on 3 prior launches, all of which were at lower temperatures. Similarly on Columbia, there were foam strikes on every single space shuttle mission, and the external tank foam that came off this big piece that hit the orbiter, that actually happened on 7 launches, and if you extrapolate tonight, probably 12, so 1 in 10. But NASA started to sort of accept that as being an acceptable failure that the spacecraft could tolerate, even though it wasn't designed that way. And by this point, most of the designers had retired or died. In that case, 40 years later. So. Normalization of deviance, I think, is a very interesting sort of way to think about the design and operation of these spacecraft, and hopefully the cultures at places like SpaceX and Blue Origin are trying to learn those lessons. Wayne Hale, who was the shuttle program manager at the time of the launch integration manager at the time of the Columbia accident, read that book and thought, after a 30-year career at NASA, viewed it as the best book that every engineer should read to understand the profession of engineering.
And he didn't read it after Challenger. He read it after Columbia, even though it was published 10 years before.
We will have time for one more question, please, and then we'll give each of the panelists an opportunity to give us a final thought.
Thank you. Lori Gordon with the Aerospace Corporation. I think we worked on Apollo, not me, but way back then. So given the environment we're in now, commercialization of space, this idea, fail fast across the development life cycle, acquisition life cycle of the V, if this was the environment in which Apollo was grounded in, how would that program have evolved differently given the current space we're an environment we're in today?
A companion to the previous question, this entrepreneurial culture, same, different. Today, she invokes the fail fast mantra of today's entrepreneurial culture. Was that true then? If it weren't, would it have been different? David, as an entrepreneur.
Certain of the aspects of the fail fast mantra and certain of the aspects of today's entrepreneurialism are well suited to software-based systems. And I think that as those software-based cultures try to find their way into the world that aerospace inhabits every day, which is mission critical, life critical, big dangerous stuff moving fast, it's having difficulty adapting, right? Which I think is one of the great contributions of the aerospace industry in general, is like it's full of people who know how to build big dangerous things that can hurt people and how to do that safely. And if I do a Google search and I get the wrong answer, no big deal, as long as one of the top 20 is right, fine. Fly-by-wire system can't work that way, and I think around driverless cars and other things, you're seeing that struggle today. I also think, and it was mentioned earlier, the question of risk is a really important one, because when you go back and look at the Apollo mission, there were risks that are just kind of jaw-dropping today. For example, if one of the astronauts got hurt on the lunar surface, they were basically going to die there. There was no way for an injured astronaut to get back up the ladder, even with the help of the other astronaut. There was a solar storm soon after the Apollo missions that probably would have killed them, and was just dumb luck that it didn't happen when that happened. And there were many, many other single-point failures. And then you look at Columbia and Challenger accidents, and people say, well, spaceflight is risky, which is true, although those accidents are both human organizational accidents, really, and not so much based on the inherent risk of spaceflight. So I actually feel that if, well, I guess we have now committed to a new lunar program, or really any new human spaceflight program, a public conversation with Congress about what's acceptable in terms of risk, because airline safety level of risk is just not feasible to get these projects done, and nor is it really what the astronauts themselves expect in some way. I had a conversation with John Grunsfeld, who did a number of the Hubble repairs, and the last Hubble repair was considered extremely risky because of the state that the shuttle program was at and other things that were learned, and he went ahead and did it. And afterward I said to him, were you aware that it was that risky? He said, of course, it had been discussed. And how did you feel about that? And he said, well, I felt like I was personally contributing to the expansion of our knowledge of the universe, and I'm a scientist, and that science to me was worth a fairly high level of risk of my life, right? And that's a conversation that needs to be had, and I think many astronauts do have it, about they're not expecting airline level safety. They're not expecting the safety you expect from your automobile, and neither should we as a public and a constituency for human spaceflight. Or if we want that level of low risk, it's going to cost many times what it would cost otherwise. And yet, there's the sense that somehow NASA has to make it safe because the consequences of an accident are so severe politically and programmatically for them. I think the consequences of incompetence in those accidents are severe. But the consequences of an accident where you really didn't see something and you really had something new that was really anomalous and dangerous, or a risk that was calculated and known and just taken. One of my favorite quotes from Wilbur Wright, of all people, is, the risk that is taken knowingly is infinitely better than the risk that's taken unknowingly and recklessly. And so I feel like as we go into a new era of human spaceflight, a public conversation on that risk and the public ethics around that risk is essential. Otherwise, you're going to get drowned in redundant, complex systems that are never going to go off the ground.
As I suspected would be the case, there is a lot more that this panel could say. More questions, I'm sure, could come from the audience, but it's 12:30, unfortunately. I'm going to ask each of the panelists to give us a final thought. Again, among the 6 more hours of content you would like to share with us, if there's a final thought to put a capstone on our discussion here, I'd appreciate hearing it. Why don't we go from right to left and finish with Teasel? John?
Well, only that Apollo was a unique period, and the geopolitical forces that caused this program to have the kind of support it did within Congress, and the continuity of that support was essential. And it's often linked to the president and the leadership. Kennedy originally wanted the landing in '67. It was actually Bob Seamans that added the language to make it before the decade is out. It's not clear we've had that leadership since. Many presidents have made proclamations about going back to the moon or going to Mars. I think at least 4 or 5 have, and none have followed through with the level of political support that would culminate in the budgets to actually do that. So I don't think that can be funded entirely privately by private enterprise or entrepreneurs.
David?
I think, people, especially where I work at MIT, very fond of talking about engineering as problem solving. Engineers like to solve problems, which is true and it's important. But I think what really drives a lot of great technology is much more engineering as a form of self-expression on the part of engineers. And I think of engineers as philosophers who articulate their view of our place in the world by the things they build. And my favorite thing always about Apollo is that it was basically useless from a straight utility point of view. Wasn't solving a problem that somebody had on Earth. I think of it as a giant piece of performance art and a expression of the engineers who built it and how they saw ourselves in the world. And I think 50 years later we really see that was the value of it. And the value of that, of course, again, it took 30 years, but as a inspiration, cultural watch point, source of other people doing other comparable things. Again, we're only beginning to understand those effects, and we should think about many other types of engineering projects in that vein more than in what's the ROI and how would I solve this problem tomorrow, which is important, but not ultimately what drives the really great innovation.
Jack?
It's shameless promotion.
You're entitled.
This book, Safely to Earth, The Men and Women That Brought the Astronauts Home. I wrote this because the team that I work with on both Apollo and Space Shuttle were maybe a total of a couple of hundred, but they were all people below the radar. We know about the astronauts. We know about the people who were on mission control, but we don't know about the other 400,000. And I worked with a couple hundred of those, and I gave them faces and I gave them names, and I wanted you to see them. And you could see what was going on at that level and how things were changing, so that they themselves will have. And one of the things my publisher did is actually in the index flag them by name and what pages they're on and what they did. So these are people that could now hand this thing to their grandchildren and say, see, on page 44, I was talked about doing X. And it's their personal and professional lives. Beyond that, I have a section in the back called Questions I'm Often Asked About the Space Program. One of them is about Space Shuttle, Challenger, and Columbia. One of them is, did we fake the moon landing? So there, in the back is all these things that I get asked all these times that you can now have at least my answers to. Anyway, that's it. Thank you.
Thank you. And Teasel?
So we've talked quite a bit about how critical industry was to making Apollo a reality, to achieving that goal. But I think it's also important to note that it's part of the reason why Kennedy proposed Apollo in the first place. And he asked Lyndon Johnson to find him a space program that would be highly impressive, that we could win. And Johnson had conversations with a lot of people in NASA, and also when he was speaking to people from the Department of Defense, they said this would demonstrate American industry, the robustness of a capitalist society, and that was going to be critical to fighting the Cold War. And so when we think of industry's role in Apollo, we should also remember that part of the reason why Kennedy proposed it, part of the logic of Apollo is showcasing American industry.
Yeah. Well, I thank the panel. I thank Don. I thank Bob very much, and all of you for coming. I hope we have shed some light on a comparatively unremarked piece of the great celebration that we as mankind all can enjoy this week. Thanks very much for coming.